Hey everyone, my name is Taylor Sparks, Editor-in-Chief at Integrating Materials and Manufacturing Innovation. I've got a brand new paper to talk about, which has to do with 3D printing and how we optimize the process of setting just the right parameters. This comes to us from researchers Mojumder and coworkers at Northwestern University, Washington State University, and MIT. Now, I'm guessing everyone here has already tried 3D printing things at some point, and you know that there's a lot of parameters to pick. There's the temperature, the print speed, the layer height, right? Now, setting the exact values for these to optimize printing is such a common problem that we actually set this up for a recent Bayesian optimization tutorial using Honogumi. This is a well-known problem, and we're looking for solutions, something better than trial and error to fit these parameters more accurately. Something that they put forward in this work, which is really interesting, is not just Bayesian optimization, but rather using a surrogate model. It says right here, the study uses it using a physics-based thermal model for this process using GPUs to accelerate the finite element method. So this is interesting. Jumping into the paper, it talks about a limited number of materials being able to print because it's just hard to predict these things ahead of time. It's hard to know which parameters to set things to, and if you don't get them right, it can lead to layer adhesion issues or residual stresses or shrinkage or bad mechanical properties. This is sort of well known. And it's also a known thing that you can use surrogate models, right? You could use simulations to predict parameters. It's just that these are usually pretty computationally expensive, which can be costly and time consuming. So one of the cool things they've done here is they actually have a GPU accelerated thermal solver that does high fidelity simulations of the temperature evolution and cooling rates and does so at pretty low computational cost. It says it simulates this process by varying parameters like the nozzle temperature, print speed, bed temperature, layer height to come up with cooling rate data. And then it uses a Gaussian process regression as your surrogate model to then go about predicting. So what does their model actually use, right? It's actually pretty complex. Like here's an example of the physical model that they use to simulate heat transfer. They're considering all the things, right? Convection, radiation from the filament, convection radiation from the print bed. You've got conduction between the filament and the print bed, conduction between the deposited filament and the heated bed itself. One of the key parameters that they think is going to be important in their Gaussian process model is this cooling rate. And they show how they're actually able to calculate the cooling rate. It says right here, it's calculated by taking the difference of the temperature last crosses the crystallization temperature, 100 degrees for PLA, in the thermal history to nozzle temperature and the time required to reach that final crystallization temperature for the deposit time. Ultimately, using this approach, they can explore a large design space where they're looking over the different height, the speed, the nozzle temperature, and then compare how it would do with random search. If you were just trying randomly to get the right settings, it shows you, the cooling rate, how it's sort of all over the place. But here, they're actually able to learn how to predict the cooling rate very effectively with this approach using a low-cost simulation data of your thermal properties. So check it out in the latest issue of IMMI.